the three previous presentations we discussed the current state-of-the-art measurement techniques, so CFD, wind tunnel, and track testing with power meters. And with the Ring of Fire, we would like to make an addition to that, namely on-site technique that is also able to visualize the flow field. So that answers a bit the question, what is the Ring of Fire? Well, it's a system that performs on-site full-scale aerodynamic drag measurements on an athlete in the field, so while cycling on a track or on the road. In the same time, we make quantitative flow visualizations in the wake of the athlete, and then based on with PIV, particle image velocimetry, and then we can relate this flow visualizations that we have to the drag force. That's the main concept. So how do we get this drag force from the Ring of Fire? Well, we, as you see in this animation, we take a few velocity fields. We measure a few velocity fields upstream before passage of the cyclist. We measure velocity fields in its wake, and then we set up a control volume. A different way of looking at it is in this frame of reference, where we have our cyclist moving at a constant velocity uc. We measure our environmental velocity field, and we measure our wake velocity field, and then we set up a control volume, a momentum balance, where if we take the flow fields upstream and downstream of the cyclist far enough away, we can neglect the pressure term. We are left with this equation where you see it only depends on the environmental velocity field, the wake velocity field that we measure, and the cyclist velocity, and the density of the flow. Yeah. So this idea of the Ring of Fire, it actually came around in 2015 by Shakitano et al., who imagined that the use of helium-filled soap bubbles could increase the scale of PIV measurements, and that we would be able to perform on-site measurements on a full-scale cyclist. In 2017, Terra et al. Performed the first proof of concept study, so to say, to see if this idea of the Ring of Fire would actually work on a small scale sphere of diameter 10 centimeters. I will not go too much in detail in those results, but I will mainly focus in this presentation on the 4 experiments that we have done with cyclists. And so the first experiment that we have done with a real-life cyclist was in the back of our in the back of our lab with a party tent. We set up a tunnel to confine the bubbles. We let our cyclist pass through there at 8 meters per second, which is around 30 kilometers per hour, in both time trial and upright position. So you see him here in the video passing in upright position. And then we let him pass 10 times in each position. And we acquired that at 2 kilohertz, the data, because at that point in time, we were still not 100% sure which data would be interesting for us. So we tried to measure as much as possible. The downside of measuring such a high frequency is that we gather a lot of data, and to store that data, to transfer it from the camera to the computer, it took about 5 minutes per run, per measurement. So that's not ideal for future applications where if you want to do a measurement on a track, you would ideally do a measurement every 20 seconds. Then looking into some results of this experiment, we got first the flow visualization. First, we compared to literature, and we saw quite some good agreement there to wind tunnel tests. And then we looked at the development of the wake. Development of the wake over time, and we saw, as we expected, that the peak velocity, the peak deficit in the wake decreased over time, and the wake broadened over time. Where we didn't expect that in the far wake, our field of view would be too small and the wake would go outside of the field of view. So that was already a learning point number one. And then here below you see a nice visualization where we see some vortices and then velocity planes over time in the wake. Converting these velocity fields to drag gives us then we see that for the upright and the time trial position, we actually see that we can actually measure the distinct variation. So we expect high drag for the upright case and a lower drag for the time trial case for the arrow position. And then when we compare this to literature values, we saw that we are at least in the right region of drag. So we are actually measuring the correct amounts of drag. But yeah, okay. So we still see that there is a plus minus 5% of uncertainty, which is rather high. So we want to repeat this experiment and in a more controlled environment to see if we could reduce the uncertainty on these measurements. So we did a second experiment, and as you see from the video, it was already a bit more professional. We increased the size of the tunnel to reduce the blockage. And in this time, we used a low-speed PIV system, since we learned from the previous experiment that if we have a measurement plane every meter or 1.5 meters, we would have enough data for drag computation. We let our cyclists pass at 5 meters per second, which is a bit on the low side for professional cyclists, but as you can see, the sports hall was not that big. So this was basically really the speed limit was limited because of the size of the sport hall. And then we repeated the same configurations, time trial and upright, and we had about 30 runs per position this time. And because we used a low speed system, already our time per run was about 2 minutes, reduced to 2 minutes. If we then compare the drag values of this indoor experiment on the left here to our outdoor experiment, which I present on the right, we see that we again capture the difference in upright and time trial position. And by going indoor to a more controlled environment, we already reduced the uncertainty to plus minus 2.5%. I have to say here that the fact that the average drag is different is we use different bike and different cyclists in both experiments. So we only look at the deltas and at the uncertainties here. So okay, for this experiment, we already reduced it to 2.5, plus minus 2.5%. And then again, we compared it to literature values. And the previous experiment where I showed you that the ring of fire was in the right area of drag values, I chose two studies that were close to our results. If we now take a larger set of data from literature, we see that there is, first of all, there's quite a spread in the literature, but our ring of fire data, however, falls nicely in that spread of drag values that we see in literature. However, we are still a bit on the low side of the velocity spectrum. So the next thing we wanted to try was two things with the next experiment, and that is, can we determine, first of all, where the uncertainty is coming from? So what is influencing this 2.5% plus minus 2.5% uncertainty? And second of all, can we perform simultaneous power meter measurements, so the track measurements that Harm was talking about before? And can we then give a direct comparison to simultaneously acquired power meter data, so that we have a better comparison than in the previous slide where we compared to this bunch of data, which is all with different cyclists, different methods. So we performed a third experiment, again indoor, again low speed. We used the same tunnel. In this ice skating hall, we were able to go up to 8 meters per second again. And then like the previous two measurements, we wanted to see, okay, can we still capture the large scale aerodynamic changes, but also can we now capture small scale aerodynamic changes? So we tested time trial and upright again, and then in time trial position, we tested the aero helmet that you see in the video, and we used also a normal road helmet. And we were interested if we could measure that drag variation. And here we have about 50 runs per position. And since we added a triggering system, we could just let our cyclist ride continuously through the hall, and then every time he passed, we could do a measurement, which was about every minute, every half a minute, 2 minutes. So if we then have a look from our sensitivity analysis or from the uncertainty, we saw that the most important PIV processing parameter was the size of the integration window. So we see that if we are too small, from smallest to biggest that we tested, we see that the uncertainty really grows. And we saw that the sweet spot there is between 5 to 25% of the characteristic length scale. But maybe even more important here, what we found out is that when we apply a dedicated wake contour and we only measure the wake of the cyclist, only the velocity of in the wake of the cyclist, we get, and we apply conservation of mass, we get actually the most accurate drag measurement. So we don't take into account all these small fluctuations in the environmental velocity, which in the end adds up to quite some error. If we then compare these results to our power meter, we see that we capture the same, so we can capture both the large scale as well as the small scale variations, and we are in the same reach at the same deltas as measured by the power meter. However, the power meter model is highly influenceable by the settings that you choose on the rolling resistance, etc. And then to quickly round up, because I think my time is almost finished. Our fourth experiment, which was already talked about by Harm, was the drafting experiment, where we now tested both individual riders as well as drafting, so we could see how much drafting reduction of how much drag reduction was found by drafting in both lateral and longitudinal positions. We went at 13 meters per second this time. Again, we went to 1 kilohertz acquisition because drafting gave us a few extra complications. Namely, if we needed to compute the drag here, if you want to compute the drag for the first cyclist, you would need this control volume, and the second cyclist, you would need controlled volume from the plane in the middle and the back. So we needed this velocity plane in the middle, in between the two cyclists. And because then we cannot choose a control volume that is far away from the cyclist, we also needed to include the pressure term. Some minor issues which we found is that when we want to capture this field in between the cyclists, we really get the shadows of the trailing cyclist, which we then needed to remove with some extra processing. So there was an extra processing step in between for the drafting cases. And this plot, I can skip it. We can discuss if there are questions about it, because Harm already discussed most of it. So with that, I would like to thank you for your attention, and I'm open for questions.
Thank you, Alex, for the presentation. Let's see if there are already questions in the chat. Yeah, there's a question saying that the outside environment is not completely outside, since there's the tent, and also apparently some sidewalls before the tent. Have you assessed the influence of these?
We have not assessed the influence of the tent itself. The tent, so first of all, the tent is mainly there to confine these bubbles. Otherwise, they would fly away. And the opening. So if you see in this picture also, we open and close the tent before and after passage of the cyclists. Except from the first experiment where the tent was a bit small and we had quite some blockage. All the other experiments we chose the tent so big that there was a blockage ratio of about 3%. And then we assumed that there was no influence further from those walls of the tent. I don't know if that answered the questions a bit.
Yes, thank you.
Okay, next question is how do you see the possibility to commercialize such a system? Yeah, or if that's not possible, if you don't see that possibility, would it then remain a research tool?
I think in the future, for sure, there is a possibility to commercialize this. But before we are arriving there, I think it will mainly stay a research tool, because now there's still a lot of expensive equipment needed, and for example, the seeder of the bubbles, there are only a few of them in the world. But so first, I would say the acquisition system, so that the PFE system, the bubbles, need to be become a bit more easily available, I would say, and then there is for sure the possibility to commercialize this product.
Maybe I can add a small comment there. So in this project, we are collaborated with LaVision, that is a hardware manufacturer, well, hardware and software manufacturer for flow measurements, and they are planning to commercialize it. Well, first for automotive. And eventually that could be also commercialized for cycling. But indeed, the system does require, well, it's not cheap, first of all, because it requires quite some advanced equipment for PIV, and does require quite some user expertise.
Thank you.
Right, then the other questions have to wait for the lunch.
Or Alex, you can also answer these questions in the chat there, and then maybe you can have a more detailed discussion in the chat.
Good point. Thank you, Andrea, and thank you, Alex, for the presentation. Then we go to the next speaker,